All right, welcome. This is 8.3 trig equations. So we will be solving trig equations using the unit circle and just using definitely identities and algebraic methods. So start with a little warm-up. This says solve equations involving a single trig function. All we want to know is if the radian values are a solution to the equation. So this says, is pi over 4 and pi over 6, are these solutions to 2 sine theta minus 1 equals 0? Well, fair enough. All you do is plug in pi over 4 and pi over 6 for theta. So that's where we'll start. Let's say at theta equals pi over 4, you get 2 sine of pi over 4 minus 1 equal to 0. Sine at pi over 4, make sure you have your unit circle out. Sine at pi over 4 is square root 2 over 2 minus 1 equal to 0. And then the 2's cancel. You get square root 2 minus 1 equal to 0. And we get that square root of 2 equals 1, which is definitely not true. This means that pi over 4 is not a solution. So theta equals pi over 4, not a solution. Okay, then we try pi over 6. And theta equals pi over 6, you get 2 sine of pi over 6 minus 1 equal to 0. Sine at pi over 6 is 1/2. You get 2 times 1/2, which gives me 1 minus 1 equal to 0, and 0 equals 0. That checks out. So this means that pi over 4 is a solution. Not pi over 4. Pi over 6 is a solution. Okay, that's it. That's as simple as that. Plug in the radian value and see if the equation holds true. Okay, next. Solve the equation cosine theta equals 1/2. Give a general solution for all the solutions and list 8 of the solutions. Okay, so we are going to make the general solution. This means we need to make a solution that will cover all radian values that make cosine 1/2. So what we first have to think of now is what radian values of theta on our unit circle make cosine 1/2. And if you're looking at your unit circle, this means that one value of theta that makes cosine 1/2, positive 1/2, is pi over 3. And then I'll make 2 columns here. We're going to need 2 columns. Okay. And then another radian value on the unit circle that makes cosine a positive 1/2, not 2 pi over 3, not 4 pi over 3, but it's going to be 5 pi over 3. Okay, so these are the 2 radian values that makes cosine 1/2. But now we have to cover the general solution. This means that we need to make a formula that represents every pi over 3 and that represents every 5 pi over 3 infinitely. And the way we do that is we think of the revolutions or the period of cosine. So all we have to do here is say, all right, theta equals pi over 3 plus 2 pi k. Because 2 pi is the revolutions of cosine. And k represents any integer, which means we do the same over here. Plus 2 pi k. Now these are called the general solutions, right? That's a general solution, and that is a general solution for theta. Now all it wants us to do is list 8 solutions. This means we get to pick values for k. And you get to pick whatever values you want for k. It does not matter as long as k is an integer, right? K has to be an integer. Let me write that down somewhere. K is any integer. And remember, to be an integer, you are a whole number from negative infinity to positive infinity. That's why I said when it wants 8 solutions, pick whatever number you want for k. Pick 1, pick 0, pick 100, pick negative 1000. No matter what, that's still going to be a solution for theta. But we want to keep it simple. And let's start with, well, k equals 0. Sure. That's where we'll start. We'll start when, I'll do that here. We'll say k equals 0. This means that if k is 0, you plug in 0 for that k, and we get theta is equal to pi over 3. Same thing over here. If k is 0, then theta equals 5 pi over 3. Look at that. 2 solutions so far. Now let's go back. Let's make k equal to 1. Now we have some fraction work. Theta equals pi over 3 plus 2 pi. Because we plugged 1 in for k, and then that just became 2 pi. All right, put 2 pi over 1, get a common denominator of 3. Our second value for theta is going to be pi over 3 plus 6 pi over 3. So what's that? 7 pi over 3. There you go. Okay. There's our third solution, actually, right? And then we do it again. Plug in 1 for k over here, and you'll get theta equals 5 pi over 3 plus 2 pi. Put 2 pi over 1, get a common denominator of 3, and you'll have 5 pi over 3 plus 6 pi over 3. So that's 11 pi over 3. All right, that's 4 solutions, 4 more to go. Now, let's let k, that's not k, let's let k equal 2. This means you'll get theta equals pi over 3 plus 4 pi. Okay, put 4 pi over 1, get your common denominator of 3, pi over 3 plus 12 pi over 3. Pi over 3 plus 4 pi, 12 pi over 3 gives me 13 pi over 3. That's was not those. Sorry. Rocking back and forth and annoying me. Okay. There we go. And again, theta equals 5 pi over 3 plus 4 pi. Put that over 1. Common denominator of 3. 5 pi over 3 plus 12 pi over 3. You get 17 pi over 3. Okay, there's 6 solutions. Let's keep going. 2 more. Last one. K equals 3. Theta equals pi over 3 plus 6 pi. Put that over 1. Common denominator of 3. Pi over 3 plus 18 pi over 3. 19 pi over 3. Same thing over here. Theta equals 5 pi over 3 plus 6 pi over 1 multiplied by 3 over 3, 5 pi over 3 plus 18 pi over 3. What is that? 23 pi over 3. And there you go. We have our 8 solutions. One, 2, 3, 4, 5, 6, 7, 8. There you go. Okay, so that's how you make a general solution. If it doesn't give you restrictions, then you spit out how many answers it wants. This one, 8 solutions, so that is the general solution for all 8 solutions. Okay. All right, let's keep going. Now we want to solve these trig equations by using the general solution, but this time we were nice and we only want solutions within the unit circle, 0 to 2 pi, right? That's the unit circle. Okay, so we handle this like we did the last one. This is the sine of 2 theta. And we want to know, just imagine that all of this is theta right now. We want to know where on the unit circle is sine equal to 1/2. What radian values get me to 1/2? And that answer would be theta equals pi over 6. And again, I can split this up. And also theta equals 5 pi over 6. And now we make the general solution. We go by the revolutions, the period, the cycle of sine, and that is every 2 pi k. 2 pi k. But we are forgetting something. this wasn't theta, it was 2 theta. So all we have to do is put a 2 in front. Put a 2 in front. 2 theta equals pi over 6 plus 2 pi k. So this 2 theta goes right there, right? Goes right there. Okay, now we have the general solution, but now we have to solve it for just theta. So that means divide everything by 2. Or even better, multiply everything by 1/2. Because if you divide everything by 2, I mean, that one's going to be a little messy. This one's going to be fine. So, however you want to do it. If you want to make it neat, we could say, let me get rid of that. I could say 1/2 times 2 theta equal to 1/2 times pi over 6 plus 2 pi k. Which probably looks a lot neater, but if you divide by 2, you'll get the same thing. So now we get our new general solution of pi over 12 plus pi k. Plus pi k. And same thing over here. 1/2 times 2 theta equal to 1/2 times 5 pi over 6 plus 2 pi k. You get theta equals 5 pi over 12 plus pi k. Okay, so these are your, I want to cover that trouble. These are your general solutions. And now it wants to know what are the actual solutions that belong on the unit circle. So we'll plug in values for k to figure that out. And we're going to have to determine if we are over a revolution or under revolution. But it's probably best to always start out with k equal to 0. Okay, so we plug in 0. If you plug in 0 for k, we get theta. Oh my goodness. Theta equals pi over 12 and theta equals 5 pi over 12. So those are definitely in the unit circle. Pi over 12 is in quadrant 1, and I think 5 pi over 12 is still in quadrant 1. Yeah. Because 6 pi over 12 would be pi over 2. So yes. So still going. K equals 1. This means we would have theta equal to pi over 12 plus pi. Put pi over 1. Common denominator of 12, and we get pi over 12 plus 12 pi over 12, so 13 pi over 12. Same thing over here, 5 pi over 12 plus pi. Put pi over 1. multiplied by 12. And we'll get 5 pi over 12 plus 12 pi over 12. So 17 pi over 12. All right, still going, because 13 pi over 12 and 17 pi over 12 are still within our unit circle. All right, because 18 pi over 12, let's see, what would that be? That'd be 3 pi over 4, something like that. Yeah, because if you had to get to pi, yeah, 12 pi over 12 would be pi, and 13 pi over 12, and 17 pi over 12. I think those are in quadrant 3. So we're still good. Okay, then if we're still good, keep going. K equals 2, and theta would equal pi over 12 plus 2 pi. Put that over 1, multiplied by 12. We would get pi over 12 plus 24 pi over 12. That would give me 25 pi over 12. And we can stop there because 25 pi over 12 is out of our unit circle. And the reason I say it's out of our unit circle, just step back 1 radian. If we step back 1 radian, 24 pi over 12 is 2 pi, which means 25 pi over 12 is over. So we don't use that one. Okay, so we stop there, which means we have our solutions. And our solutions are pi over 12, 13 pi over 12, 5 pi over 12, and 17 pi over 12. Okay, cool. All right, perfect. All right, do it again, same thing. So first thing we want to do is see all of this inside as just theta, right? See all of this inside as theta. And we want to know where on the unit circle is tangent equal to 1? What radian value on the unit circle makes tangent 1? A positive one. And that radian value is going to be pi over 4. And also not 3 pi over 4, not 5 pi over 4, but actually, yes, 5 pi over 4. 5 pi over 4. Okay. And then we have to think about the revolution, the period, the cycle of tangent. And tangent repeats itself only every pi k plus pi k. Okay, but again, we are forgetting something. This wasn't just theta. This was theta minus pi over 2. So that's what that becomes. So this theta over pi over 2 must replace this. So that's the next step. So now we have theta minus pi over 2 equal to pi over 4 plus pi k. Same thing over here. That must replace that. So that becomes theta minus pi over 2 equal to 5 pi over 4 plus pi k. Now, just clean it up. Add that pi over 2 over. So theta would become pi over 2 plus pi over 4 plus pi k. Same thing over here. Theta would be pi over 2 plus 5 pi over 4 plus pi k. Okay, still going, because we're still making a general solution. Combine pi over 2 and pi over 4. What's that become? 3 pi over 4? Yeah, 2 over 2, 2 pi over 4, 3 pi over 4. So our general solution is going to be 3 pi over 4 plus pi k. Over here, add a pi over 2, that's 2 pi over 4 plus 5 pi over 4, that should be 7 pi over 4 plus pi k. These again are your general solutions. General solutions. Okay, so those are the general. Now let's find solutions within the unit circle. And the first thing we'll do is we'll let k equal 0. And if k is 0, then we get theta equals 3 pi over 4, and theta equals 7 pi over 4. Perfect. Those are within the unit circle. Then let k equal 1, and theta will be 3 pi over 4 plus pi. Put that over 1, common denominator of 4. You get 3 pi over 4 plus 4 pi over 4. So hey, look at that. You get 7 pi over 4, what we have above. So we have a solution that's repeated. That's okay. Now over here, theta is 7 pi over 4 plus pi. Put that over 1, common denominator of 4. You get 7 pi over 4 plus 4 pi over 4. That gives us 11 pi over 4. Can we use 11 pi over 4? Is that within the unit circle, 0 to 2 pi? No. Again, if you step back some, 8 pi over 4 is 2 pi. This means that 11 pi over 4 is definitely over, which means that we cannot use this. It's over, which means we stop, we're done, and our only solutions here are 7 pi over 4 and 3 pi over 4. That's it. Okay. Not bad. Okay. All right. Still going. Same thing. Let me see. Yeah, we're still doing general solutions for these, and then those will change. Okay. All right. Once again, see all of this as theta. See all of that as theta. And we want to know what value of theta makes cotangent negative square root 3 over 3. So we have to think about this for a second. Pi over 6 is square root 3 over 2 and 1/2. And pi over 3 is 1/2 square root 3 over 2. And cotangent puts cosine puts x over y. So if we were going to do that, you would have square root 3 over 2 over 1/2, which would be by 2 over 1, which gives us the square root of 3. That's what we're looking for. If you did it the other way, 1/2 over square root 3 over 2, that would be by 2 square root 3, which would give us square root 3 over 3, which is what we're now looking for. Okay, so we kind of have what we want. And we know that it's going to be a pi over 6 radian value, but it's also going to be negative. So we now think, what radian value of pi over 6 makes cotangent negative? And that should be 5 pi over 6, because that's in quadrant 2. And then it should be 11 pi over 6. Because that's in quadrant 4. Okay, and now, before we plug that in for theta, cotangent is just like tangent, repeats itself every pi k. Repeats itself every pi k. All right, but again, it wasn't theta, it was 2 theta over 3, so that goes in for theta. So you have 2 theta over 3 equal to 5 pi over 6 plus pi k. Same thing. This goes in for that theta. And this becomes 2 theta over 3 equal to 11 pi over 6 plus pi k. Okay, and now we just want to solve for theta, so we have to make this look clean. You can divide everything by 2/3 or multiply everything by the reciprocal, 3/2. That's what we'll do here. We'll say 3/2 times 2 theta over 3 equal to 3/2 times 5 pi over 6 plus pi k. Same thing over here. 3/2 times 2 theta over 3 equal to 3/2 times 11 pi over 6 plus pi k. Okay, and the result is theta equals, what's that, 15 pi over 8, or that is, let's see, you cross cancel, that's 1, that's 2, so you get 5 pi over 4 plus 3 pi k over 2. Over here, theta equals, again that's 1, you get 11 pi over 4 plus 3 pi k over 2. Okay, well, 11 pi over 4 is over our revolutions, so we won't use the second formula. We won't use the second general solution. So here's this, and there's that. But since 11 pi over 4 is over, we won't use this solution. We'll just use the first one. Which means we'll start. We'll say k equals 0, and theta will equal 5 pi over 4. There's that. That's in the unit circle. Then we'll say k equals 1, and we'll get theta equals 5 pi over 4 plus 3 pi over 2. Common denominator of 2, you get 5 pi over 4 plus 6 pi over 4. That gives us 11 pi over 4, which happens to be, again, over. So our only solution here is just 5 pi over 4. That's it. Hey, that was nice. Okay. Last one. Do it again. Yeah, let me make mine half, so I know. Okay, cool. Okay, so again, we look, consider all of this as theta. Consider all of this as theta, and we ask ourselves, what value of a theta makes cosine 1/2 on the unit circle? And that value of theta is pi over 3. Plus cosine's revolutions, 2 pi k. Again, over here, where is cosine positive 1/2 again? And that would be theta equals not 2 pi over 3, not 4 pi over 3, but theta would be 5 pi over 3 plus 2 pi k. But remember, it wasn't theta, it was theta over 3 minus pi over 4. So that goes in for theta. So that becomes theta over 3 minus pi over 4 equal to pi over 3 plus 2 pi k. Same thing on the right side. So you get theta over 3 minus pi over 4 equal to 5 pi over 3 plus 2 pi k. And clean up. Okay, add the pi over 4 over. Theta over 3 equals pi over 3 plus pi over 4 plus 2 pi k. And then theta over 3 equals pi over 3. So pi over 3 plus pi over 4, or 7 pi over 12 plus 2 pi k. Then, to get rid of that 1/3, multiply both sides by 3. So 3 times theta over 3 equal to 3 times 7 pi over 12 plus 2 pi k. And you'll get theta equals 7 pi over 4 plus 6 pi k. There's one general solution. All right, now let's go fix this one. So theta over 3 equals 5 pi over 3 plus pi over 4 plus 2 pi k. Theta over 3 equals 5 pi over 3 plus pi over 4. You get 23 pi over 12 plus 2 pi k. Then multiply both sides by 3. (23 pi over 12 plus 2 pi k). And we get theta equals 23 pi over 4 plus 6 pi k. And there's our general solution. But we can't use it because 23 pi over 4 is definitely over the unit circle. Okay, perfect. So I think we know what our only solution is. Let k equal 0, and you'll get theta is 7 pi over 4, and that's it. If you choose 1 for k, it's going to put our first general solution over. So that's it. That's where that one finishes. Okay, so that's how you make general solutions. Okay. Now again, let's say that these restrictions of 0 to 2 pi weren't here. Let's say that those were gone. Then yes, you could find infinitely many solutions because we don't care if it's within the unit circle. So that would be just like the very first problem. But here, we make your life easier. We give you restrictions, and we only want radian values inside the unit circle. Okay, excellent. All right, so these ones are definitely a lot nicer. These ones say solve a linear trig equation. So we treat it as a linear algebraic equation, and we only want values again within the unit circle, 0 to 2 pi. Okay, so our job here is to solve for sine. We are solving for sine theta in this one. So that means subtract the 3 to the right side. You get 2 sine theta equals negative square root of 3. Then divide by 2, and sine theta equals negative square root of 3 over 2. And now, all we have to ask ourselves is, on the unit circle, from 0 to 2 pi, what radian values make sine negative square root of 3 over 2? And those radian values are going to be 4 pi over 3 and 5 pi over 3. That's it. 4 pi over 3 and 5 pi over 3. That's all we want. That's it. Those are so much easier, right? Okay. Do it again. Here we're going to solve for cosine. Okay. Here we solve for cosine. Okay. So first thing you do, add the 3 over. 4 cosine squared theta equals 3. Then divide by 4. Cosine squared theta equals 3/4. Then you will square root both sides. And you'll get cosine theta equals, don't forget the plus or minus, square root 3 over 2. And again, we ask, what radian values on the unit circle make cosine a positive square root of 3 over 2 and a negative square root of 3 over 2? And if you're looking at your unit circle, those radian values will be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And that's our answer. Don't forget the plus or minus when you square root. Okay, moving on. That was it for that page. Now this one. Solve a trig equation, quadratic in form. So we can, again, we want to solve for values on the unit circle. Now this is quadratic in form. And remember, when we say quadratic in form, we mean that this equation looks exactly like ax squared plus bx plus c equal to 0. Which means, depending on the equation, it can possibly be factored. You see how we bring all this algebra into it. So it can possibly be factored. So let's take a peek. 2 sine squared theta minus 3 sine theta plus 1 equal to 0. Well, this one will definitely factor. And I will rewrite it so you can see it. If I wrote this as 2x squared minus 3x plus 1 equal to 0, this means that this would factor to 2x minus 1 and x minus 1 equal to 0. 2x squared, negative 2x, negative x, negative 3x plus 1. But now, all you have to do is replace all of these x's with the sine function. And we're there. So this means that this becomes 2 sine theta minus 1 times sine theta minus 1 equal to 0. Now, since this is factored, set each term equal to 0. 2 sine theta minus 1 equals 0. Sine theta minus 1 equal to 0. We get sine theta equals 1/2. And sine theta equals 1. Now, again, we pop up that question. Let's look at the first one, though. Let's look at this one. We say, what values of theta on the unit circle make sine equal to 1/2, a positive 1/2? And that's going to be pi over 6 and 5 pi over 6. So there's 2 answers. Then let's look at this one. We say, what radian values on the unit circle make sine a positive 1? And that answer is going to be pi over 2. There you go. That's it. Okay. Perfect. All right. B, it's already factored for us. So let's go ahead and set those equal to 0. Set that equal to 0, set that equal to 0. You'll get cotangent theta equals -1 and cosecant theta equals 1/2. Cosecant theta equals 1/2. Okay, well, let's look at the first one. Where on the unit circle is cotangent a -1? And that's going to be at 3 pi over 4 and 7 pi over 4. There's our solutions there. Next is, where is cosecant equal to 1/2? Well, my friends, that's going to be nowhere, right? So remember, for cosecant, if you're looking at the unit circle, cosecant likes, which one is pi over 6, right? At pi over 6, the coordinates are square root 3 over 2 and 1/2. So cosecant is the reciprocal for sine. So this means that cosecant at pi over 6 would be the reciprocal of that 1/2, which means it would be 2. Which tells us that nowhere on the unit circle is cosecant ever going to be 1/2. Okay, but another way to prove this is by inverses. We could say, apply, what is it? If apply those formulas we made in 8.2. So I could say theta equals the inverse cosecant of 1/2. Which means, by those inverse formulas, this would be the same as the inverse sine of 2. Remember those reciprocal formulas we made with the calculator? Well, if you type this in your calculator, guess what you're gonna get? Domain error. So, for this cosecant function, the theta value is no solution. Proven by the unit circle and proven by the inverse formulas we made in 8.2. Okay, perfect. Okay. All right. So now solving trig equations using identities. So here we have 3 cosine theta plus 3 equal to 2 sine squared theta. Of course, we want all our values on the unit circle. Okay. So before we start, remember the big identity, the main one, cosine squared theta plus sine squared theta equal to 1. Hey, stop. Okay, so with that being said, we will use that identity to help solve this trig equation by identities. So this means that sine squared, if I rewrite this, this becomes 3 cosine theta plus 3 equal to 2 times the identity for sine squared. Sine squared is known as 1 minus cosine squared theta. And this comes from manipulating that identity's formula or equation. So this means we have now put it all in terms of cosine. So let's go ahead and solve this, or first rearrange it. So 3 cosine theta plus 3 equal to 2 minus 2 cosine squared theta. Now I'm going to take everything on the right side and move it to the left. Okay, so here I'm going to get 2 cosine squared theta plus 3 cosine theta minus 1 equal to 0. Right over, subtract 2, good. And now does this factor? And that answer is yes. Let's see. 2, that shouldn't be minus 1, that should be plus 1. Watch your signs. I subtracted the 2 from the 3, so I get a positive 1. Okay, so now this becomes, if we factor it, 2 cosine theta plus 1 times cosine theta plus 1 equal to 0. Then set it equal to 0. You get cosine theta equals -1/2, and cosine theta equals -1. Hey, that's the fullback there. Yeah, I know. It's pre-cal, but okay. Now we ask ourselves again, where on the unit circle is cosine equal to -1/2? And that's going to be at 2 pi over 3 and 4 pi over 3. And where is cosine equal to -1? That is just at pi. There's our solutions. Okay, not bad, right? That's by identities. So remember that identity, that's the main one. You can manipulate it many ways. Remember, we manipulated it to become 4 or 5 equations off of that, 4 or 5 identities. So just know you can do that. Okay. Then, same thing here. All right. Cosine squared theta plus sine theta equal to 2. Well, let's go ahead and change this all in terms of sine. This becomes 1 minus sine squared theta plus sine theta equal to 2. Okay, so you get 1 minus sine squared theta plus sine equal to 2. I'll move everything over to the right side. I want my sine squared positive, or I could just divide everything by -1. Doesn't matter. I'll just say I move everything over to the right. So if I move everything over to the right, I get 0 equals positive sine squared theta minus sine theta plus 1. Okay. Now, does this factor? Well, let's find out. If I rewrote this as x squared minus x plus 1, are there any factors of 1 that can make negative 1? And that answer is no, right? So if we can't factor something, we can always complete the square. Oh, I know, you didn't expect that coming, did you? So before we complete the square, let me just make one thing sure. I'm going to make our lives easier. We're going to say that x is sine theta. That's our little substitution, okay? Okay. So this means that we are going to have to complete the square to solve this. Okay, well, with that being said, let me go ahead and rewrite this as x squared minus x plus 1 equal to 0. This is already in the perfect form to complete the square, which means I move the 1 over. X squared minus x equals negative 1. And then I am ready to complete the square, which means I will take half of the middle term's coefficient, right? Half of the middle term's coefficient. So this is to complete the square process. So I'm going to say CTS, and you're going to have negative 1 over 2 squared, which gives me 1/4. I don't even need parentheses on that anymore. That's just 1/4. And then we add that to both sides. So you would have x squared minus x plus 1/4 equal to negative 1 plus 1/4. And now this side becomes factorable. You have x minus 1/2 squared equal to negative 3/4. And then after we do that, we would square root both sides, but we run into an issue here. You get x minus 1/2 equal to plus or minus. What happens here? The square root of a negative gives us imaginaries. Which means that you would have I square root 3 over 2, which means we cannot move on. Because this is imaginary, which means that theta will have no real solutions. Sorry, guys. It happens. Okay, perfect. That's how we solve trig equations. We apply identities when needed, and we just apply algebra. It's strictly algebraic, as you've seen that. Factoring, square root method, all of that good stuff. So that's how we solve these. Next is the calculator method. Solve a trig equation with a calculator. I'm going to take a quick break. Okay. All right, these are a little tricky to work with, okay? We want to apply the inverse trig functions to these, but the tricky part is staying within the unit circle, 0 to 2 pi. Okay, so that's the tricky part. So the first thing I want to do is find out the tangent theta of -2. Tangent theta equals -2. So we need to find that radian value. Well, the only way to find that radian value is to apply the inverse. So this means that if we apply the inverse to this function, we'll get theta equals the inverse tangent of -2. Okay, but here's where the tricky part comes in. Remember, the inverse tangent lies on the interval -π/2 to π/2. So if I draw the unit circle for that, maybe more room. If I draw the unit circle for that, here's -π/2, and here's π/2. There's 0. So what this means is that, remember, the inverse tangent lives in quadrant 1 and quadrant 4. In quadrant 1, the inverse tangent is positive. In quadrant 4, the inverse tangent is negative. So that means that places the inverse tangent of -2, that places our angle below 0. So this places our angle of theta below 0. So this means that it is below 0 to 2 pi. So I'm going to put that. So I'll say theta is under 0 to 2 pi. Which means that we have to fix this. We have to take this theta and put it back into the unit circle, 0 to 2 pi. Well, the only way to do that is to think of tangents cycle. And tangent repeats itself every pi. So to put this back into the unit circle, we will add a value of pi. So this means that this theta, I'm going to add a unit of pi. This means that this should put me in quadrant 2. So what I'm doing with this is I'm saying that theta value plus pi. Theta plus pi. So that's how we're going to fix this. So in order to get it back into the unit circle, we're going to say that theta, actually this, I'm going to say solution 1. Solution 1. We're going to say that theta equals the inverse tangent of -2 plus pi. And if I do that, I'll get the answer of, to 2 decimal places, I'll get the answer of 2.03. 2.03. And what's also good to notice about this, actually I'll do that one in maroon, because this is now that angle. Okay, so what's also, like I said, what you should notice about this is that since we went to quadrant 2, since our value of tangent is negative, well, in quadrant 2, tangent is also still negative. So that's why this works. Okay, but that doesn't mean we're done, because is it possible to stay in the unit circle and get another value for tangent that is negative? And that answer is yes. In order to get that other answer, well, I'm going to have to take this value of theta again and add another pi. So, or we come back to this theta and add 2 pi. So I'll show you how it works first. Now this angle is going to come right back here. So this means that this value of theta gets added on another pi. So we're just going to say theta plus 2 pi. And I'll just extend this green line over here as well. And that's going to give us our second solution. And the only reason it's a solution is because now we're in quadrant 4. We're still in the unit circle. And in quadrant 4, tangent is still negative. So, solution 2. You get theta equals inverse tangent of 2 plus 2 pi. And that's going to give me 5.18. And I'm going to put that in green because now that's the value of that theta. And of course, check your work. Now if I say the tangent of 5.18, I should get somewhere close to -2, right? So I'll say check work. I'll do that in this color. Check work. Let's say just the tangent of 2.03 and the tangent of 5.18. These both will get me back to -2. So it works out. Okay, pause one more time. Okay, perfect. All right, let's keep going. Had to send my other class an email because this pre-cal lesson is going into my next class. So good thing we have 2 questions left. Okay, let's do this again. Solve the equation sine theta equals 0.4 on the unit circle. So once again, apply the inverse. We're going to say theta equals the inverse sine of 0.4. So second inverse sine 0.4, that gives me 0.41. And remember that the inverse sine function lives on -pi/2 to pi/2. Okay, now remember, we're looking for values on the unit circle still, 0 to 2 pi. So let's draw the unit circle again. Okay, make most of my room. And here's the unit circle. Down there's -pi/2. Here's pi/2 and 0. Well, sine of 0.4 gives me a positive 0.41. So this means that our theta is in quadrant 1, which is perfect because that means we are in 0 to pi, 2 pi. Now, the other question is, how do we get another positive value of sine? So how can we get one more solution, okay? Because one's already fixed for us. Solution 1 is theta is 0.41. That's in quadrant 1, which is perfect. Now we have to figure out, how do I get another positive value for theta? Well, remember, sine is only positive in quadrant 2. So this means that we need to get this value of theta into quadrant 2. And the only way to do that is, well, we can't add a pi, because if I added a pi, that would put me here in quadrant 3, where sine is negative. And if you added a 2 pi, that would give you 1 whole revolution, and we'd be back in quadrant 1, but we'd be over revolution. So we can't do that. So the only way to fix this is, well, here's pi. Instead of adding a pi, we will subtract a pi. So for solution 2, we get that theta will be pi minus the inverse sine of 0.4. So for this one, we did pi minus theta. So if I do pi minus the inverse sine of 0.4, yep, I get 2.73, which is this angle right there. There you go. That one wasn't too bad. And again, I can check my work. I can say the sine of 2.73 and I get 0.4. I can say the sine of 0.41 and I still get 0.4. So this checks out. Okay. Last one. All right, use a calculator to solve the equation. Secant theta equals -4. Okay, between 0 and 2 pi. Okay, so we apply the inverse. That's where we start. Theta equals the inverse secant of -4. And remember our formula. We made the inverse calculations, so this becomes the cosine inverse of -1/4. The cosine inverse of -1/4. And cosine inverse of -1/4 is 1.82. And remember, this is on the restrictions 0 to pi. So 1.82 on the restriction 0 to pi. Okay. Now, let's draw our unit circle. Here's 0, here's pi. And if my value of cosine, so if my theta, let's see, if it's -4 and needs to be negative, this means that when I say cosine of 1.82, I get negative. Okay, so this means that since we are negative, we must be in quadrant 2. So that's fine. We have one solution already. So my first solution, solution 1, is theta equals 1.82. Okay, so there's solution 1. But now we need a second solution, and we need that solution to be negative. So where else is cosine negative? Cosine is also negative in quadrant 3. Cosine's also negative in quadrant 3 because cosine's positive in 4 and cosine's positive in 1. So our question is, how do we get the angle to be in quadrant 3? Well, with that being said, if we try the trick of adding a pi, if I add a pi, this will put me in quadrant 4 where cosine is positive. And we need cosine to be negative. So adding a pi is not going to work. What if you add a 2 pi? If you add a 2 pi, we come back here, which means that we would be in the same quadrant, but we would be over our unit circle restrictions. So adding a 2 pi is not going to work. What about subtracting a pi? If we subtract a pi, then this means I'd be in quadrant 1, where cosine's positive. That's not going to work. So what if we instead subtracted a 2 pi? So this is 2 pi. So in order to get this angle into quadrant 3, I must say 2 pi minus theta. 2 pi minus theta. That's how we do it. So this becomes solution 2. I get theta is going to be given by 2 pi minus the inverse cosine of negative 1/4. And that should give me 4.46. This represents that angle. And that's it. See, a little tricky. We have to know inverse restrictions, and we have to figure out how to get the angle back into the quadrant to keep the same sign, positive or negative. Okay, that is it. That is 8.3. Next is identities on 8.4, and it can probably get a little crazy there. Okay, guys, see you later.